Chapter 6 Chemical Equilibrium. Section 6.2 Equilibrium Constants of Pressures. We can calculate the standard Gibbs energy of reaction given K sub P, the equilibrium constant of pressures, and vice versa. We can calculate K sub P given the standard Gibbs energy of reaction using this simple equation. The standard Gibbs energy of reaction is equal to negative RT times the natural logarithm of K sub P. We derived this equation in the previous section. So now let's look at one example. Let's look at this chemical reaction. The reactants are A and B. The products are X and Y. Now the expression of the equilibrium constant of pressures is this. We have products on top, reactants on the bottom. And don't forget about the stoichiometric coefficient for every single species. For example, when we look at product X, it has to be Px over P naught raised to the power of its coefficient nu x. Same for Y, A, and B. Again, products on top, reactants on the bottom, and we take care of the coefficients. In this case, P is unitless because every single term is unitless. When we do Px over P naught, we cancel the unit. Now let's look at one numerical example problem, 6.2.1. Let's say the partial pressures of A, B, and X are 0.1, 0.2, and 0.3 at the chemical equilibrium of this reaction at room temperature. Calculate the equilibrium constant of pressures and the standard Gibbs energy of reaction. So first, we can compute K sub P. We'll just use this kind of expression. We have products on top, reactants on the bottom. We have only one type of product, which is X on top, A and B on the bottom. We have 2X, therefore this 0.3 over 1 bar should be squared. We have 2A, so we have 0.1 bar over 1 bar squared. We have only 1B, so we have this guy to the power of only 1. And on top we have 0.09, on the bottom we have 0.01 times 0.2, and the result is 45. That's the numerical value for this K sub P. And this does not have any unit. Now let's compute the standard Gibbs energy of reaction. It's just negative RT times the natural logarithm of K sub P. We plug in the numbers. It's just negative R is 8.3, temperature is 298. We take the logarithm of 45, we'll get a negative number. It's going to be negative 9,400 joule per mole, and I convert it to kilojoule per mole. We can also calculate K sub P given delta G, standard Gibbs energy of reaction, using this equation. Again, K sub P should be unitless. It's always unitless. Now let's look at another numerical example problem, 6.2.2. We're now given the standard Gibbs energy of formation of these two chemicals, N2O4 and NO2. I think this is dinitrogen tetroxide, and this is just nitrogen dioxide. Sometimes you can say mono nitrogen dioxide, but I'd rather just say nitrogen dioxide. That's clear enough. We have the values of their standard Gibbs energy of formation at room temperature. Now we have this reaction. Assuming this reaction has reached equilibrium at room temperature in 1 bar, now we can calculate the partial pressures of these two chemicals. How do we do that? First, we need to compute the standard Gibbs energy of reaction. 2 times the Gibbs energy of formation of NO2 minus 1 times the Gibbs energy of formation of N2O4. So 1 and 2 are just the coefficients over here. And then we get 4.81 kilojoule per mole. That's the standard Gibbs energy of reaction. Now we can compute the equilibrium constant of pressures for this reaction. And it's e to the power of negative delta G of R over RT. We plug in all the numbers, and then we get 0.1437. And that's the value of K sub P. Now we will express K sub P in terms of the partial pressures of NO2 and N2O4. Because the total pressure is 1 bar, over here it says 1 bar, then we can just use a variable. We say NO2 has a partial pressure of X bars, then N2O4 must be 1 minus X bars. Now we have NO2 on top. Because it's the product, it's going to be squared, so we have x squared on top. On the bottom, it's going to be just 1 minus x, because the coefficient in front of N2O4 is only 1. So we have this equation. When we look at this equation, we can simplify this bar and bar cancel, bar and bar cancel, and now we have a quadratic equation. X squared is equal to 0.1437 times 1 minus x. Well, this is simple enough to solve. X is going to be 0.314, and 1 minus x is going to be 0.686. You may wonder, this is a quadratic function, we should have two roots or two solutions. Well, this is one of them, the other one is negative, and we cannot have negative pressure. So this is the legitimate solution to the problem. Now at the room temperature, if the total pressure is 1 bar, then the partial pressures of N2O4 and NO2 are 0.686 bar and 0.314 bar.